Good evening. Welcome to this live session on NPTEL course on hydraulic engineering. So we'll continue with our problem solving session related to the topic of flow through pipes. Okay. So we'll directly start with the problems. The first problem that we'll discuss is again a very big problem. It's a simple problem but involves a lot many parameters. Okay. So the question, as it says, there is a horizontal pipeline. Okay, there is a horizontal pipeline which is 50-meter long. A horizontal pipeline 50-meter long is connected to a reservoir at one end and discharges freely into the atmosphere at the other end. Okay, for the first 25-meter length from the reservoir, the pipe has a diameter of 15 centimeter and it has a square entrance at the reservoir. The remaining 25-meter length of the pipe has a diameter of 30 centimeter. The junction of the two pipes is in the form of a sudden expansion. The 15 centimeter pipe has a gate valve whose value of K is zero point 0.2 in fully open condition. If the height of the water surface in the tank is 10 meter above the center line of the pipe, you have to estimate the discharge in the pipe by considering Darcy-Weisbach friction factor F as 0.02, and you have to include all the minor losses. Okay, you have to include. Normally in the question it is given that you have to neglect the minor losses, but since it is a very critical problem, they have asked you to include all the minor losses. So as I have always said, it is the first part is to visualize with the form of a problem figure. So basically, what is the first line? There is a horizontal pipeline which is 50-meter long. So this is a 50-meter long horizontal pipeline which is connected to a reservoir at one end. Okay, so this is the reservoir at one particular end and this is the 50-meter long pipeline. Okay, for the first 25-meter length from the reservoir, the pipe has a diameter of 15 centimeter. So see, this particular pipe, okay, the pipe for the first 25-meter length of the pipe, uh, the diameter of the pipe is 15 centimeter. However, at this point, means the point where the pipe is connected to the reservoir, what is the type of opening? It is a square opening or square entrance. Okay, the remaining 25-meter length of the pipe, the remaining 25-meter length of the pipe means from here to here, that is pipe 2, it has a diameter of 30 centimeters. So this is the 30 centimeter dia pipe, this is the 15 centimeter dia pipe. Okay, it is a diameter of 30 centimeter. The junction of the two pipes is in the form of a sudden expansion. So from here where pipe 1 uh, and pipe 2 meets, at this point there is a sudden enlargement. Okay, the 15 centimeter pipe has a gate valve. So there is a gate valve, the value of whose K is 0.2, that is required for calculating the minor loss because of the presence of the gate valve. Okay, and it is in fully open condition. Okay, that's why the flow is taking place. If the height of the water surface in the tank is, okay, the height of the water surface in the tank is 10 meter above the center line of the pipe. Okay, so from the center line of the pipe it is 10 meter. You have to estimate the discharge in the pipe by considering the Darcy-Weisbach friction factor F for the pipe is 0.02, and you have to include all the minor losses. So what are the losses? First of all, there will be major loss through pipe 1, then there will be major loss through pipe 2, and then there will be minor loss. So the first minor loss is because of the entrance to pipe 1, and what is the type of entrance? It is a square entrance. Okay, then because of the presence of this valve, okay, then sudden enlargement or sudden expansion from pipe 1 to pipe 2. Then we have the exit loss when the water gets exited from pipe 2 into open atmosphere. Okay, and apart, these are the minor losses, and apart from that we have two major losses, one for pipe 1, another for pipe 2. So these are the losses. So let us see. So square entrance with a loss of head 0.5 v1 square by twice g. Okay, then valve with a loss of head. So the valve parameter, that the value of this coefficient K is given as 0.2. So 0.2 v1 square by twice g. Then head loss due to sudden expansion v1 minus v2 whole square divided by twice g. Then there is the major loss. Okay, the major loss pipe 1 and pipe 2. Now see, in the question it is given that for both the pipes the value of F is same. So we can use a single equation for Darcy-Weisbach equation where L is equal to 50 meter. Okay, but if suppose F1 and F2 are different, then for first 25 meter you have to use the F1 value, for the next 25 you have to use the F2 value. But Just to simplify the problem, in the question it is given to you that F1 is equal to F2 equal to 0.02. Okay, and then there is the exit loss, which is V2 square by 2IC. Now if you write the energy equation just as you have done in the in a problem during our last session, if you remember, we have solved a similar problem. Okay, you again take you again write Bernoulli's equation, but what are the points that you have to take? The points, see, one point you take here exactly at the exit point, and one point here. You write the Bernoulli's equation. Okay, you get the Bernoulli's equation. Okay, and based on that you will be getting a equation like this. Okay, see, I'm not explaining the part that is written here because, see, you have to write Bernoulli's equation. Now how will you write Bernoulli's equation? This is the reservoir, this is the pipeline. Okay, and just at the center line of the pipeline here, so you have to write Bernoulli's equation here, you have to write Bernoulli's equation here at this point. So if you write at this point, what is the pressure head? If you take the Gauss pressure scale, 0, velocity will be 0, plus datum head will be 10 meters, so 10 is equal to, at this point, okay, at this point, what is the pressure head? Pressure head will be 0, velocity L, there is a velocity of exit, so V2 square by twice G, plus Z2 will be 0, plus there the total head losses, okay, which you will be adding. Okay, so based on this you will be getting an equation like this. Okay, you will be getting an equation like this. Now once you have this equation, you can always substitute V1 and V2 in terms of one another, because you know D1 and D2. Okay, so from this, based on whatever substitution you have taken place, for example here V1 has been replaced with 4 times of V2, so you'll be getting some value for V2 which is 1.605 meter per second, and once you know V2, you multiply this with A2, that is pi by 4 into D2 square, you will be getting the value of discharge Q. Okay, so again this is a very important problem, because this single problem incorporates all the different losses that are possible in case of a pipeline. So you take any standard textbook on fluid mechanics and you try to practice some similar problems. Okay, it will give you confidence and it will further improve your concept on this topic. So I hope this problem is clear, and we have solved, if you remember, we have solved a similar problem in our previous session also. Let us move to the next problem. When a sudden contraction from 60 centimeter diameter to 30 centimeter diameter is introduced in a horizontal pipeline, the pressure drops from 100 kilopascal at the upstream of the contraction to 80 kilopascal on the downstream. Okay, now if you assume a coefficient of contraction of 0.65, you have to estimate the flow rate in the pipe and the loss of head due to contraction. Okay, so basically there is a contraction. Okay, there is a contraction, this is the flow direction, contraction from 60 centimeter dia to 30 centimeter dia. The pressure, now as this is introduced, the pressure drops from 100 kilopascal to 80 kilopascal, okay, on the downstream, and coefficient of contraction is 0.65. You have to estimate the flow rate and loss of head due to contraction. Okay, now if you designate a section upstream of the contraction, see, this is the contraction. If you designate a section upstream of the contraction as 1 and downstream of the contraction as 2, the loss of head at the contraction is given by HLC 1 by Cc minus 1 whole square V2 square by twice G. Okay, here the diameter 1, that is upstream, is 60 centimeter or 0.6 meter, diameter 2 is 30 centimeter or 0.3 meter, Cc is 0.65. So everything is known except V2. So HLC is 0.29 V2 square by twice G. Now if you apply Bernoulli's equation between 0.1 and 0.2, P1 by rho G plus V1 square by 2G plus P2 by rho G plus V2 square by 2G. Since this is a horizontal pipeline, we are not writing Z1 and Z2 because Z1 and Z2 will be same and they will cancel each other. Okay, and plus HLC. So from this, what will be, see, what is HLC? HLC in terms of V2 we have already obtained. V2 is known, V1 square, okay, V1 square. So sorry, V1 and V2 can be written in terms of one another because we know that A1 V1 equal to A2 V2. So P1 by rho g minus P2 by rho g gives you the difference in the pressure head. Okay, and the difference in the pressure head, say difference in P1 and P2 is given to you. There is a pressure drop from 100 to 80 because of the introduction of this contraction. So divided by rho g will give you 2.043 meter. So you simply substitute this in the Bernoulli's equation and you'll be getting the value of V2 as 5.71 meter per second. Once you know the value of V2, you multiply this with A2, you'll be getting the value of discharge. And once you know the value of discharge, see, once you know the value of V2, you can also calculate the value of head loss due to contraction. So this is a very simple problem. Okay, very simple problem. So you can say that this problem is a subset of the problem that we have already solved. Okay, the first problem, it can be said, or it can be looked as a subset of the earlier problem. Okay, sorry. Now three pipes with diameter, length and friction values of D1 L1 F1, D2 L2 F2 and D3 L3 F3 are connected in parallel between 2 points A and B in a pipeline. If an equivalent pipe DE LE FE is to replace the set of parallel pipes, you have to obtain an expression for estimating the equivalent pipe parameters. Okay, so there are three pipes such that their diameters are D1, D2, D3, their lengths are L1, L2, L3 and their friction factors are F1, F2, F3. Now when these three pipes are connected in parallel between 2 points A and B, in that case you have to obtain an expression for the diameter, length and the friction factor for an equivalent pipe. Okay, means if you have to replace these three pipes connected in parallel by a single pipe, an equivalent single pipe which gives you the same discharge, then you have to sorry, you have to obtain the expression for DE, LE and FE. Okay, that is the diameter, length and friction factor for the equivalent pipe. So what is the basic idea? See, since there is a common head drop for all the three pipes or for pipes in parallels, the head loss, the major head loss will remain same. Okay, so F1 L1 V1 square twice G D1 equal to F2 L2 V2 square twice G D2 F3 L3 V3 square twice G D3. The sum of the flows is the total discharge, that is Q is equal to Q1 plus Q2 plus Q3. Okay, then if you look at equation 1, then V1 can be written as, if you just take the first part here, okay, then V1 can be written like something like this. Okay, similarly you can write V2 or V3 also. So once you have V1, Q1 is A1 into V1. Similarly you can write Q2 and Q3. For the equivalent pipe, the discharge is, see, the discharge will have to be same, you cannot vary the discharge, that is the meaning of equivalent pipe. So pi by 4 D square V and HF head loss has to be same, FELE V square by twice G D. So for that also the discharge is this. Now if we see, look at equation 2, that Q is equal to Q1 plus Q2 plus Q3. So you'll be getting an expression like this. So this is the answer. Okay, so very simple problem. You should know what is the significance of pipes in series and pipes in parallel. So again, a point that you need to remember, you should practice some problems and have some thorough idea related to pipes in series and pipes in parallel. Okay, and let us move to the last problem for this session. A 6 centimeter dia pipe has a discharge of 450 liters per minute. At a section, the pipe has a sudden expansion to a size of 9 centimeter diameter. If the pressure just upstream of the expansion is 20 kilonewton per meter square, calculate the pressure just after the expansion. Assume the pipe to be horizontal at the expansion region. See, the problem 2, the contraction problem that we have solved today, we have seen today, it is similar to that problem. So I am giving you 5 minutes of time. Please try to look and then we will discuss the solution. Okay, let us look at the solution. So discharge is equal to 450 liters per minute. When converted to meter cube per second, it becomes 0.0075 meter cube per second. Velocity before the expansion, okay, is v1. Okay, so q by a1, the diameter of the pipe before the expansion is 6 centimeter. So q by a1 is 2.653 meter per second. Velocity downstream of the expansion a1 v1 equal to a2 v2, you can use that. So v2 is 1.179 meter per second. Head loss due to this sudden expansion is v1 minus v2 whole square by twice g. Since the value of v1 and v2 are known, you can find the value of 0.111 meter. Then you apply Bernoulli's equation between point 1 and point 2. Okay, and the pressure upstream of the expansion, that is P1, is known to you. You need to find P2. So this is straight application of Bernoulli's equation. So it is 21.73 kilopascal. Okay. So this is the session for today. Let's stop here. We will again meet next week. Thank you.